Yeah. So hi guys. So we have Dr. Pratik Tarafdar from IMSc for an interesting talk as the first talk of our online talk series from 137 Inverse, the Physics Club of either Berampur. Dr. Tarafdar will be speaking on the recent stochastic gravitational wave background discovery and his role in the discovery, in particular the Indian Pulsar Timing Array and its role, the findings. So yeah, over to Dr. Tarafdar for the talk.
Thank you so much, Abhigyan, and yeah. So first of all, thank you so much, 137 Inverse, the fine structure constant from Aizer Barahampur, for inviting me to this talk. And yeah, so I think someone is unmuted. Okay. Yeah, so thank you so much for inviting me for this talk. And I was just having a chat with the members of the 137 Inverse Club about their activities, and it's really nice that you're organizing these talks and also other outreach events to make the students aware of things happening in different horizons of science. Okay, so yeah, so I'm Pratik, and I am currently a postdoc working at the Institute of Mathematical Sciences in Chennai, and I'm a member of the Indian Pulsar Timing Array Consortium, or as we call it, the InPTA, which is an Indo-Japanese collaboration. It's not only Indian, but we have Japanese collaborators also. Our instrument is primarily Indian, which we use to acquire the data, and that instrument is the Giant Meter Wave Radio Telescope located near Pune. And InPTA is also an official member of the a greater consortium of pulsar timers called the International Pulsar Timing Array, which at the moment has 4 members: the European PTA, the PTA, the American PTA, the Nanograph, the Australian PTA, which is known as the Parkes Pulsar Timing Array, or the PPTA, named after their radio telescope, single dish radio telescope called the Parkes telescope, and the Indian Pulsar Timing Array, which is the youngest member in this whole team. Okay, so I think there is something on chat. So team members, if you find any questions on chat, please let me know. Since I'm sharing the screen, I won't be able to, I may not be able to see the chat simultaneously. Okay.
Okay,
All
like
right.
it would be better like if we keep the question and answer session at the end of the talk. Or are you okay with
Yeah, sure. So
in the mid
yeah.
of the talk?
See, I'm okay. I'm also okay with questions in the in the middle of the talk, no problem at all. But I mean, it's up to you. You are the organizers. You should decide what
Fine.
should be the best format. Okay, I have no problem if you ask me any questions in the middle of the talk as well. Okay. So that's the introduction of who I am and what are the institutes and what are the collaborations involved here. So as the title of the talk says, tuning into cosmic hum. Now, there has been a lot of news about this this announcement coming from various pulsar timing array collaborations in a coordinated way. And people have been calling it the cosmic symphony, the cosmic hum, and all sorts of names. So it's basically a background, a stochastic background of gravitational waves that we seem to have been able to receive the first hints of. Okay, now I won't call it a discovery, and I'll tell you why yet. Okay, so there are some scientific reasons, but we would still call it the first hints or the first emerging evidences of the stochastic gravitational wave background. All right. So when we look into the heavens, the skies, okay, so we have to rely when we look at the sky, we have to rely on these different kind of messengers, which bring information, different sorts of information about the heavenly bodies, the celestial bodies to us. And what are these messengers? The oldest that we have been probing has been the electromagnetic messenger in terms of light, the optical window that was opened in the 1600s by Galileo with his first telescope. And so that we know that optical light falls in the middle wavelength range of the complete electromagnetic spectrum. And it took almost 3 centuries, almost 300 years, to probe the long wavelength spectrum of these electromagnetic waves, which is the radio window. And that was opened by K.G. Jansky. And then simultaneously, we could probe the X-ray window, the gamma ray window, and so on in the electromagnetic from the electromagnetic perspective. Similarly, there are other messengers in astronomy that have emerged over the years. There is the cosmic ray counterpart, starting with the first balloon flight carrying the cosmic ray detector by Hess in 1912. And we also had the first cosmic ray detector being launched from the first EIFR campus, which was actually in Hyderabad. There is something called the National Balloon Facility in Hyderabad. So by Homi Bhabha, that was in 1932. And very recently, we have the neutrino messengers. In fact, if some of you may be aware that when this gravitational wave background announcement was made, that same day, actually, there was another very important announcement being made by IceCube, where we've got our first neutrino, astrophysical neutrino map of our own galaxy. Okay, so we have these neutrino messengers now that are used to probe different kind of things like supernova and all. And it started in 1968 by the detection from the detection of solar neutrinos. Okay, and with all these, gravitational wave messenger or gravitational messenger is the latest kid on the block, the youngest kid on the block, and the first direct detection of gravitational wave was announced in 2015 by the LIGO consortium. And these gravitational waves, like electromagnetic wave, have a complete spectrum ranging over different wavelengths. Similarly, gravitational waves are also expected to range over a spectrum of frequencies and wavelengths. So the first gravitational waves that were detected around 8 years back, those gravitational waves fall into the short wavelength window. So by short wavelength window, here we mean wavelengths of the order of kilometers. That is, if you convert it to frequencies, you would see that the wavelength would fall in the range of tens or hundreds of hertz. And the first event which was detected that was attributed, that is attributed to the merger or the coalescence of two black holes, approximately 30 solar mass. So these two black holes merged, and at the moment of merging, it was detected that there are these very strong gravitational wave signals being emitted by the system, waves with the wavelengths of the order of kilometers, and a quite high amplitude that was detectable by these instruments. So those gravitational waves which fall in the frequency range of tens to hundreds of hertz are what we call as short wavelength spectrum of the gravitational wave. Similarly, this gravitational wave spectrum is also expected to have a long wavelength counterpart, that is a low frequency counterpart. And these long wavelength gravitational waves that have frequencies in the range of nanohertz, which if you convert to distances, that would be distances of the order of parsecs, light years, okay? Around 3.26 light year is 1 parsec. So around the wavelengths of the order of light years, these are the long wavelengths that we are talking about in case of the gravitational wave spectrum. And this announcement that was made on 29 June 2023 was the announcement of the first evidences of these kind of long wavelength gravitational waves. So it's interesting that you see that when, so it took around 3 centuries to cover the mid wavelength optical window and move on to the long wavelength optical window, whereas it took around 8 years only to detect the long wavelength counterparts in case of the gravitational wave spectrum. Okay. All right. So a very brief history of the journey of gravitational waves. You can read through very many interesting books and literatures to know about the whole story. So even before Einstein's formulation of general relativity, the idea of gravitational waves was actually there, and dating back to 1865 by Oliver Heaviside. And then there were other formulations. Of course, Einstein's formulation came into being. There were other theoretical formulations for gravitational wave emissions from different kind of systems. And the detection part, that is the attempt to detect these very, very weak ripples in space-time, actually began many years back. It was a long time back. Okay, so it was in around, as you see, in 1960s, late 1950s, 60s, and early 70s. So Joseph Weber, it was this person who actually started an attempt at detecting these gravitational waves using instruments which are called as Weber cylinders. Okay, you can still see even at Oxford, I'd say. So it was his lone attempt, and he tried for many years using these Weber cylinders to see if there are very small contractions and expansions in the instrument due to the gravitational waves passing by. But unfortunately, he couldn't come up with any result with his instrument that could establish that there are compressions and expansions in the space-time manifold which is there around all of us. Okay, but then in around 1974, there was a particular astrophysical system that was discovered by two scientists, Taylor and Hulse. So they discovered a very interesting system. Back at that time, they used to call it a superstar system. So in those kind of system, you okay, orbiting around each other. So Taylor and Hulse, they discovered a system of pulsars, one pulsar and one neutron star, actually, that were rotating around each other. And this was B 1913 plus 16. It's known as the Hulse-Taylor system, or the Hulse-Taylor double system of pulsars and neutron stars. So they observed that this neutron star pulsar binary system that has a particular orbital period, each of them rotating around their combined center of mass. So this orbital period had been observed to decay with time. Okay, and this decay can be attributed theoretically to the emission of gravitational waves from this medium. So when these two bodies are rotating around each other, they are generating ripples in the space-time around them, which is propagating in the form of these gravitational radiation, gravitational emission. And this emission is carrying out energy from the system, which is causing the orbit to gradually shrink. Now, the theoretical prediction of the shrinking of this orbit, assuming that the shrinking is happening due to gravitational wave emission, so they could show that this shrinking of the orbit predicted from the theory was actually matching the observations. So this was actually the first indirect evidence of gravitational waves. Although we say that gravitational waves are detected by LIGO in 2015, but that was the direct detection. The indirect detection actually happened even many years back, 40 to 50 years back. Okay. But as I said, the direct detection of short wavelength gravitational waves, where you actually see the arm of your detector compressing and expanding in some form with the use of lasers being reflected from mirrors kept at the end of these instruments and their interference and all. So that thing was first detected in 2015 with this event, which is named as GW150914, which I had already mentioned earlier about two black holes coalescing or merging together. So that was the direct evidence. And then the first emerging evidence of the long wavelength gravitational wave background happened in 2023. So you see the gravitational waves, they have a very long history, and it's a journey of almost 1.5 centuries, almost 150 years, a bit more than that. Okay. All right. Okay. So as I said, we won't call it a discovery yet. There are reasons behind that. And why are we calling it the first emerging evidence or the first hints and so on, strong evidence and all that stuff? And why are we not calling it a detection? There are reasons, and these are a bit statistical in nature. So what we would expect to observe in order to claim that we have detected the gravitational waves is that we are looking for some particular electromagnetic radiations which we receive at Earth, and such electromagnetic radiations are required to be extremely periodic in nature. Now, one of such possible sources from which we can get very precise and periodic electromagnetic signals on Earth are these stars, which are dead stars, which are known as pulsars. Okay, now these pulsars, they are extremely massive and dense neutron stars. I would like to say corpses of stars or dead bodies of stars. that were formed after the supernova explosion, after a star had ended its life cycle. So these pulsars, these are highly magnetized and are rotating at velocities of the order of, see, like 1,000 rotations per second. Okay, so their periodicities are in the order of milliseconds. That's why these pulsars are particularly known as millisecond pulsars. So these pulsars, they emit very collimated, focused radio beams from their magnetic poles. And if their rotational axis and magnetic axis are inclined to each other, then we would expect that in case of some of these millisecond pulsars, we would be able to see the radio emission from Earth. And that would be periodic. So these radio emissions, whenever magnetic poles are inclined towards the Earth, whenever they are cutting our line of sight from the Earth, we would see these signals, okay, these radio emissions being detected by our detectors here. And as the pulsar rotates, the signal would periodically cut our line of sight. Okay, I'll show it with an animation later so that you will be able to understand better. But for the time being, just think of it that our instrument of detecting the gravitational wave background are basically some stars located at different locations in the galaxy, which are sending out very periodic electromagnetic signals in the form of radio emissions. Okay, so in order to claim that these signals carry the signature of ripples in space-time, we have to satisfy a few criteria. Now, what you see here are two very important criteria. One is called a common red noise spectrum. Another is a spatial correlation. I will tell these things later. I will explain these things later. For the time being, just understand that we need to establish these two things, a common red noise spectrum in all the pulsar radio emissions that we are observing, and a spatial correlation among the radio signals that are emerging from all these pulsars. Okay. Now we have detected these two, but there is something else, which is these are data after all, and there would be some scope of errors in your instruments or in the medium through which your signal is traveling. So these errors or uncertainties should give your results some statistical significance, and that significance has to cross a particular mark, a particular value, to claim that it is a very, very confident detection. That is, the confidence of the detection is above 98% or something like that. So right now we are very close to that hallmark, but we have not yet crossed that hallmark. So that is why we are still calling it an emerging evidence and not a discovery or detection as such. But that is only a matter of time, as we will see soon, that we will be able to claim that it's a confirmed detection. Okay, so what you see here is a spectrum of gravitational waves. So the instruments that are being used or can be used to detect the gravitational wave emissions. Right now, we have these ground-based instruments like the LIGO, Virgo, and Kagra instruments there. So these are basically interferometers. I don't know how many of you have read about interferometers, but it's simply that if you have an instrument with a particular arm and say two arms in the shape of the English letter L in the alphabet. So if you have two such arms and if you place mirrors on the ends of these arms and you make a laser beam reflect between these two mirrors, then when these arms have a fixed length, when they have a stationary length, you would expect that these laser beams being reflected by the mirrors, they would form a particular stable interference pattern. Okay. But if these arm lengths change, then obviously the distance that these lasers are traveling, that distance would also start changing. Okay. And that would cause changes in the interference pattern that you were observing when the laser beams from these two arms were superposing or adding up. So the detection of gravitational waves, which is done right now, is by looking at these interference patterns of laser beams that are traveling between the arms of these detectors. And the length of the arm of these detectors has to be comparable with the wavelength of the wave that you're trying to detect. Okay, that is a standard thing in antennas theory. So suppose at your home you're trying to watch television or whatever, any signal that is traveling in almost the radio frequency range in case of the electromagnetic spectrum, even then you know that the receiver that you need to construct in order to detect these signals should have the dimensions comparable with the dimension of the wavelength of the wave that you are trying to detect. So it is very similar in gravitational waves as well. These are all antenna. Okay. So when you are trying to detect a gravitational wave that has frequencies in the range of hundreds or tens of hertz, corresponding to a wavelength of a few kilometers, then you would need detectors that would have arm lengths of the order of kilometers. So that is exactly what happens in case of LIGO or Virgo or Kagra. Okay, so there the arm length of these detectors are around 3 kilometers, 2.5 kilometers, 3.5 or 4 kilometers. Okay, so these detectors can be used to detect gravitational waves that have a similar wavelength, and these gravitational waves that are going to cause the change in interference pattern of the lasers that are being reflected within these arms. Okay, but when we are talking about long wavelength gravitational waves, that is hertz gravitational waves, if you name them in frequency, these gravitational waves have wavelengths of the order of light years, just what I said, of parsecs or light years. Now, in order to detect these kind of gravitational waves using the same technique which is being used right now in LIGO to detect short wavelength gravitational waves, so in order to use that same mechanism to detect these gravitational waves, you will need detectors with arm lengths that are of the order of light years, parsecs. Obviously, you cannot build such detectors on Earth. I mean, a detector with an arm length of light years on Earth is impossible, not only on Earth, even space-based gravitational wave detectors that are coming up right now, like LISA. So there, even the space-based interferometers will not have arm lengths of the order of light years. You cannot. So that would mean, see, light years is like the galactic scale. So that means you need a detector that has arm lengths from one end of the galaxy to the other. So neither terrestrial non-space-based interferometers are going to detect these kind of gravitational waves. So what do we do? How do we detect these gravitational waves? Well, we can't build an instrument, but fortunately, the nature itself that has gifted us with such an instrument. These instruments are these dead stars, what are known as pulsars. Now, how these pulsars will be helping us to detect these long wavelength gravitational waves, I'm coming to that. But before that, a very small comment on what kind of systems in the universe can lead to the generation of these kind of gravitational waves. Just a very minor comment. We can have detailed discussions on this later. So in case of LIGO and all, when we are detecting the short wavelength gravitational waves, these are mainly generated by the coalescence or merger of stellar mass black holes. That is, black holes which are of the order of 20 or 30 solar mass, or mostly hardly 50 to 60 solar mass, or like that. Okay. So these black holes, when they merge, or even neutron stars, black hole or neutron star or two neutron stars, when they merge at the moment of their collision, they generate gravitational waves of very high amplitudes. Okay, and very high frequencies of the order of 10 hertz or 100 hertz. Now, these are transients. These signals will last only for seconds to milliseconds. And this is the window that you have to detect these gravitational waves, since your instrument has sensitivity to only these frequency ranges. Okay. Now, this is the kind of gravitational wave that we have been detecting, and these are generated by the neutron star mergers or black hole mergers. Similarly, the space-based interferometers like LISA that are coming up, that are going to detect gravitational wave emissions from maybe supermassive black hole mergers or stellar mass compact binaries, but these are also at the moment of the collision. However, we know that in the universe, there are numerous galaxies. If you do a very rough statistical calculation, you will find that the universe consists of around 10 to the power 11 galaxies. Okay. And all these galaxies are known to have supermassive black holes at their center. Supermassive black holes, what do you mean? Supermassive black holes that have masses. Is there a question? Okay, no. All right, so by supermassive black holes, you see that these are like black holes with masses of the order of millions to billions of sun. Like our own galaxy, the Milky Way galaxy is known to have a supermassive black hole at its center that weighs around 4.5 million solar masses. The first image of event horizon, direct image of the event horizon, which we saw in 2019 from the EHT, the Event Horizon Telescope, that is supposed to be taken from the M87 galaxy, and that supermassive black hole is like 6 billion solar mass. So every galaxy is supposed to have a supermassive black hole sitting at its center, and you have this 10 to the power 11 galaxies in the universe, and these galaxies are expected to collide with each other or merge with each other. Maybe I'm sure some of you know that our own galaxy Milky Way is heading towards the Andromeda galaxy, or from the other way, looking from the other perspective, Andromeda is heading towards us. And after some amount of time, these two galaxies will merge. So these mergers that are happening are these are happening all the time in the universe. These galaxies are merging. And when these galaxies are merging with their supermassive black holes at the center, these supermassive black holes are forming a binary system. So it's a binary of supermassive black holes, which is known as the supermassive black hole binary system. So when these black hole binaries come together and they form a gravitationally bound system, then before they actually collide and merge and form a single supermassive black hole, before that, these supermassive black holes will continue to orbit around each other for decades and decades and so. It's a very long time scale during which these supermassive black holes will keep on orbiting around each other, and their orbitals will gradually shrink, and after these few decades, they will merge. So when they merge, they are definitely going to emit very high amplitude and high frequency gravitational waves, which will end for a few seconds or milliseconds. But when this this motion, this orbiting motion is going on for decades, they are still generating ripples in space-time. And these ripples are continuous ripples. These are not transient. They are always being generated. And they are generated from each of the supermassive black hole binary pairs in the universe. Okay, so calculations suggest that we expect every year at least 10 of these galaxy mergers every year. Okay, so you see there are all these black hole binary pairs in the universe that are heading supermassive black hole binary pairs in the universe that are heading towards collision, and this whole process is going on for decades and decades and decades and so all these sources, if you think of these supermassive black hole binary pairs or the galaxies to which they belong, they are merging. So these pairs are continuously generating the ripples in space-time that are of the order of wavelengths of light years. Okay, and since these individual sources, they are generating the continuous gravitational waves, so we would expect that the gravitational waves being emitted from all these sources is adding up and creating a persistent ripple, which is always there in the space-time around us. So this is like a background. Okay, so if you think you are standing on if you imagine yourself standing on the seashore, you see waves crashing. Okay, now these waves crashing are transients. So a wave develops, it crashes. That moment you hear the sound, it's a loud noise and all that, and you're done. So you know, okay, so a wave has crashed. But now when you are going to the middle of the sea, you will see that there are very, very long waves. And these waves are always there. It's not that these waves are simply rising and they are getting destroyed. It's a superposition of all these waves, which is creating a continuous ripple all around you on the surface of the sea. So these are this stochastic gravitational wave background, which we call in scientific terms, or as GWB. This is basically the continuous gravitational ripples in this ocean of space-time around us. And that is being caused by these sources. Okay, at least we assume that it is being generated by these sources. There could be other sources also, as we would know later. Okay, so that is what is called the stochastic gravitational wave background. So far what I have told you is a very brief history of the gravitational waves, their theory, and all the efforts in their detection. The gravitational waves that we have been detecting so far, what kind of gravitational waves are those? What are their wavelengths and frequencies? What kind of sources give rise to those gravitational waves that I have tried to mention? And now this gravitational wave background that we have, we all are so excited about. What is this gravitational wave background? How is it being generated? What are the sources that could generate it, at least the astrophysical sources that we know of? And why is it that we cannot detect this gravitational wave background using the instruments that we have at present, like LIGO and Virgo? That is what I have tried to mention. Okay. So now I would move on to this part, the instruments that we use to detect these gravitational waves, these stochastic gravitational waves. So as I very briefly had mentioned about pulsars, so these pulsars are like corpses of stars, or dead bodies of stars that were formed after a very heavy star had ended its life cycle and had burst into a supernova. Then the core of that supernova had collapsed into a very massive and dense object, spherical object, which has a radius of the order of tens of kilometers. And that and is rotating at high velocities. Okay, so what kind of rotational velocities are we talking about? The rotational velocities we are talking about is like thousands of rotations per second. So that would mean that the periodicity, that is the time the pulsar would take to rotate once on its own rotational axis, is of the order of milliseconds. And that's why these pulsars, these specific pulsars that we use for long wavelength gravitational wave astronomy, these are called millisecond pulsars because of their periodicity lying in the order of milliseconds. Now, these pulsars are actually very old pulsars. Okay, see, young pulsars which were just formed after the supernova, those pulsars are a bit unstable. So their rotational velocities, they keep changing. And there could be different phenomena which can increase their rotational velocity for a moment. And again, that rotational velocity would decay and all that stuff. And these would also slow down with time. So they are basically emitting their rotational energy in the form of electromagnetic radiations, radio emissions, or even high energy emissions like gamma emissions. So when it is radiating away its rotational energy in the form of electromagnetic radiations, the rotational energy would decrease with time, which would mean that it's down with time. And after a particular age, the spin would slow down to such an extent that the magnetic field around it will not be able to power it for any more emissions. And that is when we say that a pulsar is dead. It was already a dead star, but it has stopped emitting. And that is when we say that a pulsar has gone dead. Okay, so we have these kind of very old dead pulsars in the universe. Imagine that one such very old pulsar that had stopped emitting all of a sudden finds a companion in the form, it could be in the form of a star or a white dwarf or something. And when that companion came close to the pulsar, very close to the gravitational field, then it started to pull matter from that companion. Now, this process by which matter from a companion of a binary system, in astrophysical terms, it is called accretion. Okay, so these very old pulsars, once in a while, they get these kind of companions from which they start accreting matter. And this matter, which is falling on to the pulsar, that would carry some amount of angular momentum, some amount of rotational energy. So this rotational energy again spins up these pulsars. And this time, the pulsar starts spinning extremely rapidly, getting rejuvenated from the accretion process from the companion. Now, that is how these millisecond pulsars are born. So basically, these millisecond pulsars are spun up, recycled pulsars, as we call it. And since they are usually formed by accretion from a companion, therefore, this companion would stay. If it's a white dwarf or something, it would keep staying on after the accretion has been over. And so these millisecond pulsars are usually found in binaries. Okay, and since these are rotating with these extremely high velocities, and these are old pulsars that are way past their youth, they are extremely stable, and their spin velocity or the rotational velocity periodicity, it changes with time, but at a very slow rate. Okay, so the plot which you see here, this is basically the entire population of pulsars that is known right now. Every point, every dot, triangle, or circle, or squares on these plot, it shows every pulsar that we know till today. And till today, as of today, we know around 3,500 pulsars, 3,383 or something. Okay, so that is the exact number of pulsars that we know, that we have detected till now. And among all those pulsars, only around 500 to 550 of them are known to be millisecond pulsars. That is the type of pulsars which we use for the gravitational wave background detection. Okay. So these pulsars, so on this plot, on the x-axis, what you see is the periodicity of the pulsars. That is the time taken by the pulsar to rotate once on its rotational axis. And on the y-axis here on this plot, what you see is the rate at which this periodicity decreases. That is the rate at which the pulsar is spinning down. Its spinning rate is decreasing. Okay, so in this diagram, you will see that the millisecond pulsars, they are very, very stable. Their spin down rate is very low compared to the spin down rate of the younger pulsars, which means that these millisecond pulsars are very stable. They can go on rotating at these rotational velocities of 1,000 rotations per second, around 1,000 rotations per second, for years and years and decades and decades. Okay, which makes them extremely stable rotators. And since these pulsars are emitting radio beams from their magnetic poles, like you see here, these beams are going to cut your line of sight thousands of times every second. If you have a detector on Earth, a radio telescope or something, to detect these radio beams from a pulsar in a particular direction in the sky, every second you are going to detect thousands of these pulsars cutting your line of sight. So this is like a lighthouse, an optical lighthouse that we see on the seashore. So if you are sailing in the sea on a ship and you have a lighthouse on the seashore, you will see this same exact effect called the lighthouse effect, but in the optical window, that is in case of lights. Here we are talking about it in the radio window. Okay, so this is like a lighthouse, a cosmic lighthouse that you have emitting radio emissions, throwing radio emissions towards you thousands of times every second, and at a very, very precise rate, very stable rate. If a pulsar is rotating around 3,500 times every second, say, it will keep on rotating at that same rate for a few decades. It will slow down, but very, very gradually over the length scale of decades. Okay, so these signals, these very periodic signals from the pulsars, can be used as a clock, a very precise clock. So basically, how do you measure time? You measure intervals, right, between two events. So if you are wearing a wristwatch, the second hand of your wristwatch is changing its position after a particular interval of time, which we are calling a second. So that's a measure of time that you are using. In this case, you can use the pulse intervals, the intervals between the time interval between each of the radio pulses. So these peaks when the radio beam crosses your line of sight. So each of these pulses, the interval between each of the pulses, you can use as a measure of time in that case. Or in other words, you can use the pulsar. The name pulsar itself signifies that it is emitting pulses. So you can use these pulsars as very precise clocks. In fact, these millisecond pulsars can be used as clocks with precision comparable to the best clocks that man could have made so far. Okay, so we have atomic clocks on Earth, and some of the millisecond pulsars have timekeeping precisions comparable to the best atomic clocks that we have on Earth. And these are natural, completely natural. So nature has gifted us with these ultra precise, stable celestial clocks. Okay. Now, why do we need these celestial clocks for gravity? What is the connection with the gravitational wave emission or detection of the gravitational wave emission? The connection is this. that if you have radio emission or any kind of electromagnetic emission, in this case radio emission, coming from a particular source in the sky, reaching you on Earth, and if you have, of course, you have a medium between you, that is the observer, and the source from which the radio beam is being emitted. If you have disturbances in the medium through which the electromagnetic radiation is traveling, then you would expect that radiation to reach you a little late than it would have reached you when there was no disturbance, no undulation, no perturbation in the intervening medium. Okay, this is the very basic fact that we would try to use to detect the gravitational wave background. So if you have space-time medium, of course, we have space-time medium and we have other mediums also. Now, if you have this space-time medium and it has some sort of a disturbance in it, and this light, I mean radio light, that is reaching you from pulsar, that is traveling through this medium, which itself has ripples, the medium that has ripples. So when this radiation is traveling time, it is getting slightly delayed than the time that you would expect the signal to arrive. See, as I said, that these are very precise clocks. So you know that if I have a pulse at this instant, the next pulse should reach me exactly this much time later. Okay. But you see that it's not so. You are getting that. Sometimes it is reaching you maybe 40 microseconds later. Sometimes the next pulse is reaching you 10 microseconds later. And you have all these kind of fluctuations in the time of arrival of the pulses from the pulsars. Okay, which are the pulse arrival times. So this is a probe that you can use to measure the ripples in the intervening medium of space-time. Okay. Now the question is, are these the only sources that cause delays in the pulse arrival times from the pulses? The answer, of course, is no. If that would have been the only source, it would have been easier, much easier to detect. The problem is there are other sources as well which cause these delays. Okay. So, you know, so from the Einstein's general theory of relativity, which says that massive bodies curve space-time around them, and the curvature of space-time, it tells massive bodies how to move. Okay. So in these cases, the pulsar itself is a very massive body. So it is supposed, and it's rotating. So it's supposed to curve the space-time around it. So when a beam of radio emission is generated from the pulsar's magnetosphere, and it leaves the pulsar's magnetosphere and it starts traveling towards you. In that case, the curvature of space-time around the pulsar at the very beginning, at the time of emission, is supposed to cause a certain amount of delay in the signal. Then, as I said, most of the millisecond pulsars are binary systems. They have a companion. And that is due to the fact that millisecond pulsars are born that way. They are born due to their companion. By chance, they get a companion who gives them matter and which spins them up. Okay, so most of the millisecond pulsars are binary systems. So if you have a binary companion, or by orbiting around you or orbiting around the common center of mass, then that binary companion is also expected to cause a curvature in space-time in that system. So that curvature in space-time is also expected to cause a delay in the time of arrival of the pulse, radio pulse, which is reaching you from the pulsar. Okay. Then there is even more. So this radio pulse, which is arriving on Earth, this has to travel through the galaxy, and then it enters the solar system. When it is reaching the Earth, sorry, is there a question? Okay. Please do ask if you have a question. I don't have any problem with questions in the middle of the talk. Okay. So, and even if you feel bored, let me know. So, okay. So these radio pulses, they are traveling to the Earth. While traveling on their way to the Earth, they have to cross the solar system. And the solar system, our solar system, has very heavy planets like the Jupiter. It's Jupiter and Saturn. So these very heavy planets, while orbiting around the sun, they are also causing these tremendous curvatures in space-time, which are again expected to cause delays in these signals. Okay, and remember, Jupiter has an orbital period of around 12 years around the sun. And we are talking about gravitational wave signals, which you are trying to detect, that also have these rotational periods of the order of decades. So the signature of these very heavy Jovian planets in the solar system, their orbits around the sun, are also supposed to be reflected in the delay of the radio pulse signals that you are detecting on Earth. So we need to know the solar system trajectories, the trajectories of these planets very, very precisely. Okay, and only when we know that, when we know the pulsar parameters, its binary parameters, our own solar system parameters, we would be able to tell that due to all these things, this is the amount of delay that I would expect in the signal. Now, fortunately, these are something that we know. These are what we call the deterministic terms in the delay. There are some further deterministic terms, like the clock itself, that you are using at your observatory or telescope to measure the delay. The Earth itself is rotating around, and consider those clock corrections when you are measuring time. You have to do the solar system barisector corrections. These are technical things that I won't go in here. Okay, you don't need to understand that right now. So just understand that the radio pulse which is arriving on Earth from the pulsar, that would be delayed on its way. And there are two kinds of sources of these delays. One kind of source is the deterministic source of delay, which sources we know quite well. And since we know those sources quite well, we would be able to subtract the delay contribution from those sources in the actual delay which we observe on Earth. Okay. Model these deterministic sources of delay and we subtract out these deterministic sources of delay, we would still be left with something which are the stochastic sources of delay. That is the random delays. Now, these random delays would obviously, one part of the random delays would be caused by the stochastic gravitational wave background itself, which we are trying to look for. However, this delay due to this stochastic gravitational wave background would be masked or hidden under another very, very crucial and notorious source of stochastic delay. And that source is what is known as the interstellar medium, or the ISM. These are oceans of plasma, electrons, that the pulsar radio beam has to cross before reaching the Earth. This is everywhere in our own galaxy. Okay, so we call it the interstellar medium, or the ISM. Now, this ISM, which is present between the pulsar and your receiver on Earth, that is along your line of sight, this ISM is going to cause some delays in the arrival times of the signals. What kind of a delay? These slides later. So let me just tell you about the delay. So what kind of a delay? So I don't know if you have learned about the refractive index of plasma, but forget about it. Okay, we don't need to go into the technical details. But the thing is, if you a charged medium and an electromagnetic signal, electromagnetic radiation like light or radio or X-ray or gamma is traveling through that charged medium, depending on the frequency of the signal, electromagnetic signal, which is traveling through the medium, the velocity of that electromagnetic radiation is going to change a bit. It is going to slow down a bit. This velocity is called group velocity. And so that depends on the medium which it is impinging. To be precise, the refractive index of the medium that it is impinging. And depending on the refractive index of the medium, which is basically dependent on the density of the charged medium that you have, this velocity of the signal. And it so turns out that if your electromagnetic signal traveling has a lower frequency, then those signals will be delayed more than signals traveling with a higher frequency. Okay, so the delay due to the interstellar medium in our case, or the delay due to any charged medium in the general case, which is introduced in the arrival time of an electromagnetic signal traveling through that medium, that has a 1 upon f square kind of a dependence, an inverse square dependence on the frequency of the signal that is traveling through the medium. Okay, so these radio pulses that you are observing from the pulsar, these could have frequencies in the order of hundreds of megahertz. Now, these radio beams could have also have frequencies in the order of gigahertz, 4 gigahertz, 5 gigahertz, 6 gigahertz. That is the higher frequency of the electromagnetic radiation, okay, not the gravitational wave. So there are two kinds of frequencies I'm talking about. One is the frequency of the gravitational wave in the space-time, and one is the frequency of the electromagnetic signal, that is the radio beam from the pulsar that is traveling through that medium. Okay, so this frequency I'm talking about now is the frequency of the radio beam. That could be hundreds of megahertz, that is in the low frequency range, that could be in the range of gigahertz. So the radio beams which are being emanated in the hundreds of megahertz regime, those radio beams will be delayed slightly more than the radio beams that are being emitted in the gigahertz range, that the higher frequency ranges. And that is due to the charged medium which is present between you and the pulsar, that is the interstellar medium. Okay, so this is one kind of a delay that you will face. There are other kinds of delays. The interstellar medium which is there between us, that is not a stationary medium. Okay, there will be turbulences in the medium itself, which would lead to scattering of the electromagnetic radiation that is traveling through it, and you will observe these delays due to the scattering as well. So it is almost like the twinkling of stars that you see in the sky, only that is in the optical range. You have a medium through which the light is passing, and due to changes in the density of that intervening medium, you see the stars twinkle. So that is simply lights coming in from multiple paths and forming an image on your retina, which gives you the illusion that the star is twinkling. So this is similar. In case of pulsars, only here you are not seeing light, so-called light, optical light, but radio beams, okay, using your radio receivers. And they're the same phenomena is happening. There is an intervening medium, and that has turbulences, different densities that are changing with time, varying with time, and that is causing these multi-path propagations of the radio beams, which on your receiver is creating these variable delays. Okay, so this is another source of the delay, and this is very notorious because it is known to mimic the delay that is caused by that is expected to be caused by the gravitational wave background. So once you know all the deterministic other sources of delay and you model them out, subtract them out, you are still left with a signal that would contain these different contributions in addition to the gravitational wave background contribution. Okay. However, suppose you can buy some technique, some hook or crook, you are able to, some black magic, you are able to find out what are the variations in the densities of the interstellar medium, and you are able to subtract those delay terms from your signal, and you know that, okay, now what I am left with in my signal, whatever delay I am left with in my signal is entirely due to the stochastic gravitational wave background. Even then, we would expect that if the stochastic gravitational wave is being generated by these supermassive black hole counterparts spread all around the galaxy, then the delay from one pulsar in one direction would be correlated, somehow correlated with the delay of the signal coming from a pulsar in a different direction. So suppose I'm looking at one direction in the sky, I see a pulsar and its signal, and I calculate the delay, I find out the gravitational wave. Then I look at another pulsar in a different direction in the sky. I measure the pulse arrival time from that pulsar, separate out the known terms, and even say the ISM term. And now I know the delay that I'm left with is due to the gravitational wave background. The thing is, this delay is being caused by a common background which is present among all these pulsars. So since is that the delay is being caused by a common background that is present in all between us and all these pulsars, so we would expect that the delay from one pulsar and the delay from another pulsar would have some sort of relation between them, because it is being caused by a common medium. Okay. So that dependence of the delay from one pulsar and another is something which is called a kind of correlation between the pulse arrival times of these pulsars. And it was actually theoretically worked out a very, very long time back in 1983 for the first time. There were these theoreticians, Ronald Hellings and G.S. Downes, who actually calculated the correlation and told us that if you have a pulsar in some direction, and if you have another pulsar in another direction, separated from, the distance between these two pulsars is say 10 degrees or 20 degrees. This is the angular separation we are talking about. So 10 degrees or 20 degrees or 30 degrees and so if you have say hundreds of pulsars that you have pointed out in the sky, and you are doing measurements from these hundreds of pulsars in different directions, and all these hundreds of pulsars have say 100 C2 pairs, and then all these pairs will have some angular separation between them. So if you are able to measure the delay from all these pulsars due to the gravitational wave background, then these delays coming from say two pulsars that are 10 degrees apart, and these delays coming from two pulsars that are 40 degrees apart or 120 degrees apart, they would have a particular correlation, a particular pattern. And that pattern was worked out back in 1983, and that is, after the names of the proposers, that is known as the Hellings and Downes correlation, or the HD correlation. So on the x-axis here, these are say the angular separation between the pulsars from 0 to 180 degrees. And on the y-axis, it's the mathematical way of representing the correlation between the delays from these pulsars, okay? And that would have a very specific kind of a form. This is from simulated data. So that would have a very specific kind of a form if this delay is caused by a common gravitational wave background through which the radio pulses from all these different pulsars are coming to us. Okay, so in order to establish that the delays, even after the subtraction of known delays, is due to the stochastic gravitational wave background, we have to establish that these delays also have a correlation between all the pulsar pairs that we are observing. All right. So in order to detect the gravitational wave, it's not a single millisecond pulsar that we need. We need a number of millisecond pulsars. It could be 20, it could be 30, 50, 100, whatever. More the merrier. Okay. So we need many millisecond pulsars, and we need to do measurements on the pulse arrival times of all these millisecond pulsars for many years. 5 years, 10 years, 20 years, many, many years. We need to do the measurements. Because the delays due to gravitational wave will show up only on a long time scale. These are very long wavelength gravitational waves, that's why. And when we have done the measurements, we have to correlate these delays among all these pulsar pairs. If that delay shows this particular pattern among all the pulsars, only then you can say that, okay, this delay was being caused by the stochastic gravitational wave background that theoreticians had proposed long back. This is exactly what we had been running after for so long. All the PTA pulsar timing array. It presently consists of pulsar timing array units in USA, which is called nanograph. In Europe, they have 5 radio telescopes which have been observing a number of pulsars for around 24 years. In America, they have been observing it for around 15 years, a number of pulsars using Green Bank telescope and Arecibo, which is unfortunately not there anymore. Okay, and also now Chime in Canada and all that. In Australia, they have the Parkes radio telescope, which is now called the Parkes Muriang radio telescope in honor of the Aborigines of that place. So that Parkes telescope had also been observing a number of pulsars. Of course, the sample is different because the pulsars that you see from the southern hemisphere are not the same that you see from the northern hemisphere. So these are different sets of pulsars they have been observing. So USA has been observing for like 15 years. European PTA had been observing for around 24 years now. Okay, PPTA had been observing for around 18 or 20 years, I think. And the Indian Pulsar Timing Array is the latest member. And our first official data release, which happened last year around October, that is a data set of around 3.5 years. We are a very young PTA, okay? So we had been observing our own set of millisecond pulsars. Now it's almost 5 years that we have been observing, and we will come up with the new data very soon. So all these PTAs, and including other new emerging PTAs, which are still not a part of the International Pulsar Timing Array, like the Meerkat, which is in South Africa, that is an meantime it's an emerging PTA. There is a PTA in China called the CPTA, Chinese PTA, who use this fantastic instrument called FAST, which is right now the largest non-steerable, that is fixed, single dish radio telescope in the world. Okay, so so they use this FAST to make pulsar timing measurements from their own sets of pulsars. So they are also emerging PTAs who may join the IPTA very soon. Anyway, the South African team is already contributing their data to the International Pulsar Timing Array. So what I mean to establish is that there are hundreds of radio astronomers all across the globe, and theoreticians, and statisticians, and data scientists, cosmologists, who are working together to detect the delays in pulse arrival times from millisecond pulsars for a very, very, very long time, over decades. So that is our data set. And the InPTA, as I said, it's a very new PTA. I need not go into all these details. Okay, you can check out our website, or we can have a chat later if you want to know more. But what I would like to emphasize upon is the Indian PTA uses this unique instrument called the Giant Meter Wave Radio Telescope, which is located in a place called Khodar near Narayanganj, 80 kilometers from Pune. Okay, so this radio telescope, it's not a single dish radio telescope. Firstly, it has 30 antenna, 30 dishes. Each dish has a 45-meter diameter approximately. Okay, and these are like these 30 parabolic reflectors that are spread over a huge area, where the maximum distance between two of the dishes is around 25 kilometers. Okay, so this is and this 30 radio telescopes are actually arranged in a Y shape. So it's a Y array, a Y kind of a shape of an array, and all these 30 telescopes together, if they are tuned properly, all these 30 telescopes, radio dishes together, can act as a single radio telescope. The technique of interferometry, as we call it. That's basically tuning all these together in a very specific and precise way, such that all these together act as a single unit. So this uGMRT, this was the vision of Professor Govinda Swarup, because of whom you can see here. So because of whom we have this telescope now. But the uniqueness of the uGMRT lies in the fact, there are other interferometers. The uniqueness of uGMRT actually lies in the fact that it observes radio frequencies at very low scales. Okay, the other PTAs, nanogravity PTA and PPTA and all, they observe radio frequencies above 1 gigahertz range. In our case, in the Indian PTA using the uGMRT has receivers which can do observations from as low as 200 megahertz, 150 to 200 megahertz, all along till 1 or 1.5 gigahertz. So it's the lower radio frequency range that we can cover using the GMRT, our own Indian instrument. And why is this low frequency observation important? It is important because of this, what I explained to you, the interstellar medium, the very notorious ocean of plasma, which is lying between us and the pulsars. The delay effects due to that medium, due to that ISM, is most prominent at lower radio frequencies, which is due to this relation I said, that when you have a medium, charged medium, and an electromagnetic signal is passing through it, most of the delay, most of the deviation would be caused at for the lower frequency signals that are traveling through it. So when you are observing low frequency radio signals arriving from the pulsar, you can see the effects of delay due to the ISM most prominently in your data. And those effects are much less prominent at higher radio frequency pulses, which you observe, which the other PTAs have been observing. In the InPTA, we observe low frequency radio pulses. So we get the maximum amount of ISM delays in our data. It's also very messy because there is a lot of noise. When you're observing low radio frequencies around hundreds of megahertz, you are very much likely to fall into the purview of communication satellites which are going around. That would cause noise in your data. That could simply wash off your signal. Then you can have very high tension electrical wires radiating at comparable radio frequencies. You can have even a microwave or a television, ruining your job. So that's a nuisance when you are actually doing observations at lower frequencies. So at GMRT or around GMRT, it's a radio quiet zone. We try to keep it as radio quiet as possible. And we do these observations at these very low frequencies. And also, the interesting thing is, as I said, all these 30 antenna can work together as a single telescope. Similarly, in around 2017 and 2018, there was an upgrade in the GMRT, an upgrade that actually allowed us to divide all these 30 antenna into a number of separate groups, or as we call them, sub-arrays, technically. So technically, you can have around 4 subarrays, a maximum of 4 subarrays right now, into which you can divide these 30 radio dishes, and you can tune each of these subarrays separately to do observations in different frequency bands simultaneously. Which means that I am observing one particular pulsar in the sky. Now, one thing what I can do is I can use all the 30 radio telescopes to observe that source at a particular frequency range, say 300 to 500 megahertz. Okay. But I can also divide my 30 antennas into 2 groups with the suitable number of telescopes required for different frequencies. So I can divide these 30 antenna into 2 different groups. And with each group, I can observe the same source, the same pulsar, at different frequencies. So one set of antenna can observe the pulsar in, say, 300 to 500 megahertz range. Another pulsar, another subarray or another set of antenna, they can observe the same pulsar at the same time, simultaneously with the other subarray in a different frequency range. Say 1 gigahertz to 1.5 gigahertz, which is slightly higher. Okay, so you can do very low frequency observations and mid-frequency radio observations of the same source simultaneously. This is something which none of the other PTA telescopes right now in the world can do. This can only be done by GMRT in India. So we have low frequency advantage and we have multi frequency band simultaneous observation advantage. Why it is an advantage that I will tell you now. But before that, from the organizers, let me know how much time I have. I think I'm overshooting and I don't want to bore all of you.
Oh, I guess you can go on. You can for the completion of the talk. It's anyways very interesting and engaging. Yeah, you can go on. There is no time restriction per se.
Okay. Thank you. Thank you so much. But yeah, if you feel bored, just let me know. I mean, if it is interesting, I'm very glad. If you are getting bored, just let me know. I'll stop. Okay. All right. All right. So why is this multi-frequency observation, simultaneous multi-frequency or simultaneous multi-band observation very important? The thing is, as I showed you earlier, that we know that there are some deterministic sources of delay in the signal. Sources which we can theoretically model. Okay, it could be the pulsar curvature due to the pulsar in space-time, curvature in space-time due to the pulsar binary. It could be your solar system heavy planets. It could be your clocks, whatever. All these are known sources. Okay. Similarly, when you are looking at the delay due to interstellar medium, even there are some deterministic terms. It is not that all of it is random, all of it is stochastic. It's not like that. So when I'm talking about this kind of a delay, that is, we call it the dispersive delay. And this phenomena of lower frequencies getting more delayed, this is called dispersion, coming from the dispersion relation. That's why it's called dispersion. So these kind of delays are actually theoretically modeled. So you see that if you have a signal coming at some frequency f1, and if you have a signal coming at some frequency f2, then the delay between the arrival times of these 2 signals can be calculated theoretically. simply using the dispersion relation of the medium. Okay, and in this expression, there is some constant here which you see named as dm. Dm stands for dispersion measure. So there is some constant that you have to calculate by fitting your data. You know the theory, you know the analytical form. From your data, you can see that there is some delay which you can measure. You know the frequency of the signals that you are receiving. So you know that I have a bunch of signals at this frequency, I have a bunch of signals at this frequency. So and I know that these bunch of signals at these two different frequencies are arriving at a particular delay which I'm measuring here. Okay, so since you have this expression, you have this term, you have this term, you can fit your data, fit your delay data to this particular expression to calculate the unknown constant which is lying over here in the expression. Basically, you are fitting your data to this analytical expression, the theoretical expression, and that fitting is giving you an unknown constant term which is there in your theoretical model. And this unknown constant term, which is the dm or dispersion measure, which we are calling here, this physically signifies the integrated density of the electrons along your line of sight to a particular pulsar or a particular source. So if you have a pulsar somewhere and you are looking at it on Earth, you have a line of sight between that pulsar and you, then that particular line of sight is actually cutting through different slices of the interstellar medium, right? So all these different slices, they will have different densities of the electrons, right? So you can do an integration. So if you know the density of electrons per unit length along your line of sight, and you do an integration of that density of electrons along your line of sight across the whole distance, that is across the whole line of sight, then you will get an integrated column density of the electrons which are present between you and the pulsar. This integrated column density of the ISM medium, the electrons, that is what is giving you this constant. It is constant along a particular line of sight on a given day or during one observation session. Of course, it would change because ISM or the interstellar medium is static and in a particular line of sight. It keeps changing with time. And that would lead to a different dispersion measure on the next day that you are observing the same pulsar. Okay, so when we have low frequency data, I mean, say you have you have data in 300 to 500 megahertz, and you also have data in 1 to 1.5 gigahertz, these two different frequency bands. Okay, so you do the measurements from your data, from your observations, and you find out what is the delay that you are getting in your signal after subtracting out the other terms, which you the solar system delay and everything. Once you subtract out those deterministic terms, you know that you are now left with some deterministic delay like this dispersive delay from the interstellar medium, some delay due to scattering, turbulence in the medium, some delay due to random variations in the ISM, which are stochastic in nature, which are not deterministic. You cannot determine like these kind of fixed analytical expressions. And finally, contributions from the stochastic gravitational wave background. Okay, so what you see here are basically delays in microseconds of pulse arrival times from a given pulsar. In this figure, the pulsar was named PSRJ 1909-3744. This is a particular pulsar observed on a particular day. So the MJD 59630, this is just an astronomer's way of counting days. Okay, so that's our calendar. So astronomers don't say it's 18th of August. We would say that it's a particular MJD. MJD stands for mean Julian day. So just imagine some particular event might have occurred in the past, and keeping that event as the standard or the origin, people have been counting days since then. So this observation was done 59,600 on the 59,630th day from some standard event, which is the definition of the MJD right now. So on a particular day, observation was done for a particular pulsar using the uGMRT, in two different frequency bands. So this x-axis is the frequency axis that you see, and you measure the delay in the arrival times in the 300 to 500 megahertz, which is the low frequency range, and the delay in the arrival time of radio pulses from the same pulsar on the same day at the same instant, but in a different frequency band as well, which is around 1.2 to 1.4 or 1.5 gigahertz. Okay, so these delays that you are measuring, these are measured from data that was collected in both these frequency bands on the same day at the same instant simultaneously. So one of the subarrays of your telescope was recording this low frequency data. Another set of telescopes at the same time was recording this high frequency radio data from the same pulsar. Okay, so this is what is called multi-band simultaneous observation using the uGMRT. And why it is important? It is important because, as I said, that in these delays, the other deterministic terms have already been subtracted. So I know that in this delay, the contributions that are remaining are due to the deterministic terms in the ISM, like the dispersive 1 by f squared term, which was there, some amount of scattering, then some amount of random fluctuations in the ISM, which are stochastic, and of course, the signature of the gravitational wave background, stochastic gravitational wave background, that is also here in the same data. Okay, so among those remaining factors, the next best thing that I can model and subtract is the dispersive delay, which is this expression, dispersion due to the ISM. So as you saw in that expression, the delay was a 1 by f square kind of a delay. Okay, so lower frequency is more delay, larger frequency is lower delay, and 1 by f square is a parabolic expression. And you see that same parabola kind of a thing here. So this is the parabolic trend. This is the 1 by f square trend which you are seeing here. So you simply fit your data, this trend that you're seeing, this parabolic trend, to that parabolic equation to find out what is the, since you know the frequency and you know the delay, you can do this fitting to find out the value of that constant dispersion measure, which is physically signifying the density of the ISM along your line of sight. Okay, so this is how you can actually measure the density, the integrated density of ISM along the line of sight to a particular pulsar on a specific day. And this fitting is very precise using the uGMRT only because the data points in this range of the x values and this range of the x values that you are fitting, the frequency values, they had been obtained simultaneously. Just imagine a telescope that had observed these values today at this MJD and these values 2 weeks later, okay, at a different MJD, that is this MJD plus 14 days. So that would mean that if I would have used those data points to fit for that dispersive relation and obtain the value of the ISM density, then that would not have been precise, simply because of the fact that the data points in the two different frequency ranges that I'm fitting across, those data were collected on different timescales, completely different days. The ISM might have changed by then. There might have been changes in the ISM along your line of sight in those 2 weeks. Okay, so when you are doing multi-band, say this lower 300 to 500 megahertz is one frequency band, this is another frequency band. When you are doing multi-band observations simultaneously on the same source, then you are able to do this fitting of the residuals to your analytical model of the ISM to obtain very, very precise ISM densities. That is exactly what we could achieve using the giant meter wave radio telescope in our first official data release. The Indian PTA came up with its first official data release, public data release, which was made available to everyone in the community for analysis. So in that public data release, it was published last year in around September or October. And that consisted of 3.5 years of data. Okay. And those data would include the pulse arrival times of 14 different millisecond pulsars, which we were observing across 3.5 years of timeline. So those pulse arrival delay times were made public. Also, this interstellar medium density, sort of the quantity which is actually signifying the interstellar medium density, measurement of that quantity across 3.5 years for all these pulsars, all these 14 pulsars that we had been observing, millisecond pulsars that we had been observing. And here, since we were able to determine the ISM density to such high precision, the highest precisions that had been obtained so far, due to this very high precisions, we were able to show the variations very clearly. Variations in the DM. Just imagine that your telescope is measuring dispersion measures. You are doing analysis on your data from telescope to measure dispersion measures. And your precision, that by precision, I would mean the error bars that you are seeing in each of these data points, DM points. So if you have very large error bars here, then obviously that would mean that you are unable to figure out how much has been the variation across time. Very large error bars would mean on a particular day, the value can actually lie anywhere between those error bars. So if you have very large error bars here, your variation is flat, essentially no variation. But when you are able to do measurements with very high precision, then your error bars are decreasing. Okay, so when you have smaller error bars, then you are able to see the variation. Okay, you can still say that, okay, I can do some sort of an average curve between these points, and I will see some sort of a variation only because my error bars are lower. In case of higher error bars, the average curve that you would have fitted would have been a flat line. Okay, so using the unique strength of uGMRT, that is the major role of the InPTA in this whole program, is that we are able to do, first of all, low frequency observations where the effect of the interstellar medium is most prominent. Secondly, we are able to do simultaneous multiband observations, simultaneous multiband low frequency observations, using which we are able to obtain the highest precision interstellar medium density estimates so far among all the PTAs. Okay, so when we combine our data with the data from the other PTAs, okay, when we combine our data with data from the other PTAs, what we achieve is that, say, one PTA has been observing a pulsar above 1 gigahertz or say 4 gigahertz or something, and you put in these data which are low frequency, you are able to cover a very, very wide frequency range. And when you have this wide frequency range coverage, then we will be able to do further modeling in your data to find out the remaining factors of delay in your signal. Okay, so when you are doing the delay subtraction, finally you fit for DM and you do the delay subtraction, you see that you have some delay signals which have some error bars here, and they look essentially flat, which means you have subtracted all the deterministic terms using ISM, deterministic terms from the ISM, but you still have stochastic terms. That is random variations for which you have all these error bars. They are still not giving you the amount of precision which you need to filter out the gravitational wave background contribution from this. So for that, you have to do something which is called noise modeling, which is a way of trying to theorize the stochastic variations that are expected in your ISM due to different physical processes. It could be scattering or it could be other things. There could be stochastic variations in the pulsar itself, pulsar spin itself, those kind of noises. So you have to do a theoretical modeling of these noises and do a sort of a fitting of these noise terms using statistical methods called like frequentist methods or Bayesian methods. And from that, you are going to get a distribution of the amount of noise that you can have from different sources in your data. So noise from the ISM, noise from the pulsar, and all these things. And only then, when you subtract out those noise components from your data, you could be sure that the only noise component that is remaining in my data due to the stochastic gravitational wave background. That is the only stochasticity that is remaining in my data. And then you can do cross correlation and see if you get the Hellings and Downs curve, which I mentioned earlier. Helps to model the ISM deterministic term and also to model the ISM noise. simply because it's low frequency data and simultaneous multiband data. Okay. So, so InPTA has the highest precision of DM time series reported so far. So this was, and this low frequency data can be used to study a number of other phenomena in pulsar astronomy, actually. So I won't go into the details of this. So, but there are a number of projects that are going on, and this would need low frequency radio data. So let me just skip these things. So the noise analysis part, which I was talking about when you have all the deterministic terms subtracted, you are left with only the stochastic contributions in your pulsarable time delays. And this stochastic terms could come due to your instrument itself. The instrument which you are using, obviously, none of the instruments can give you a particular measurement. When you are doing experiment in your labs, you have to report what is the plus minus error, what is the precision, and that is due to your instrumental resolution, limitations of the instrumental resolution, and of course human errors. So the systematic errors which are present in your instrument, those are going to give you some sort of a noise. Now, these noises are not correlated. These are completely, truly random. Okay? So that's why you can model these kind of systematic effects coming from your systematic errors coming from your instrument as a white sort of a noise. Okay? Now, there could be other noise sources as well. As I said, the pulsar. It's a millisecond pulsar, which is very precisely spinning and all that stuff. But still, you will have some sort of stochastic, very minor stochastic random variations in the spin itself, spin of the pulsar itself. Now, that is also one component that one has to take care of. We call it the spin noise, and it's modeled as a red noise process, an achromatic red noise process. And of course, stochastic variations due to the ISM, the DM variations, that is the density variations themselves in the interstellar medium, scattering variations, that is the turbulences, variable turbulences in the medium across these long time scales. And finally, the gravitational wave background variations which are there. Now, we are doing these observations over very long time scales, over decades or so. Okay, so it is expected that all these small noise contributions, which seem to be random, they are actually adding up over a very long time scale of observations. And this long time scale of observations, when it has all these added up noise components in them, then they are going to show a significant amount of delay. And in order to subtract that delay, you have to do the noise modeling. Okay, so as I said, there are different kinds of noise sources from the instrument, pulsar spin, and the ISM, and we have to do Bayesian analysis. No need to get into the details of that unless you are familiar with it. Some sort of, you can think of it as some sort of fitting of the data to a model, only where you do not have deterministic terms but distributions. That is the stochastic kind of equations. So you fit some distribution and you obtain some distribution. Okay. As the output. And then when you have done the noise modeling, you subtract all those known sources of noise, and whatever you are left with that has noise only due to the stochastic gravitational wave background, you do a correlation of these residual delays from all the different pulsars along the different lines of sight, and you try to see if you can get the Hellings and Downs correlation, which we had been looking for. So what actually happened? Okay, so this is the final part of the talk. Okay, I would avoid going into technical details here, but the thing is just to give you the flavor of what is this whole this craze and excitement all about. What happened? What was announced on 29 June 2023? The announcement was this: that all these different PTAs, the nanograph, the EPTA, EPTA and the EPTA jointly actually, and the PPTA, the Australian PTA and the Chinese PTA, all these PTAs individually, for the first time, showed in their data sets that they are able to see, finally, this Hellings and Downs correlation, in addition to certain other common features which are expected in the noise, which we call the common red noise, common spectrum in the red noise signal. That might be a bit technical. I would not mention that in much detail, but know that there, if you remember in one of my earlier slides, I had told you that there were at least two criteria that one needs to satisfy in order to claim that you have a stochastic gravitational wave background hint. So the first of those things, which is the common red noise spectrum, which I just mentioned, that was actually shown 2 to 3 years back in all the PTA datasets. It was already being seen with lower statistical significance, of course, but it was there. But what was missing was the Hellings and Downs correlation, which together with that common noise, red noise signal, would be a confirmatory evidence of stochastic gravitational wave background. So what happened recently is all these PTAs in their individual data sets finally claimed together that in all our data sets, we are able to see the Hellings and Downs correlation for the first time within a given statistical significance, that is some confidence interval. Okay, so where did InPTA contribute here? Obviously, I said the technical contribution. Well, the scientific contribution has been due to our low frequency data and all that stuff, simultaneous multivariate data and all that stuff. I told you why is it important to actually filter out the statistical gravitational wave background. So, but there was a challenge, which is that the InPTA data is only 3.5 years. Okay, and all these PTA observations have to be done over decades because the time scale of the variations that you are talking about in the gravitational wave background and the resultant signal, those are varying over decades. So 3.5 years of data alone cannot give you the Hellings and Downs correlation, okay, or the common red noise spectrum. So what, but on the other hand, we have this low frequency data which none of the other PTAs have. So InPTA, the Indian PTA, actually joined hands with the European Pulsar Timing Array. There were some specific reasons behind that, because the European Pulsar Timing Array had a telescope previously, which used to do some observations in 800 megahertz to 1 gigahertz range and above. But they lost that telescope in 2016. It was not actually low frequency, but at least mid-frequency radio regime was being covered. But they lost it in 2016. So they lost all these data in the mid-frequency ranges. So there we could be, we were, crucial in filling this critical gap of low frequency between the low frequency and the high frequency regimes, or the mid-frequency and the high frequency regimes. Okay. So, and the IPTA data that had a time baseline of around 24 years. Of course, all the data may not have been completely useful because older receivers would mean older systems, their resolutions would be less and all that. So actual results were obtained from a sliced down sort of a data, but that is also around 11 or 12 years. Okay, so InPTA had lower time baseline data, but very useful low frequency data. And EPTA had a longer time baseline data. However, they had higher frequency data, which is not ideal for the ISM modeling. So InPTA and the EPTA, we joined hands. Also, one more thing is that InPTA, since it is located near around the mid latitudes of the Earth, we are able to observe both northern and southern pulsars, at least to some extent. If you are sitting in Australia and if you are using the Parkes radio telescope to do observations, you'll be able to look at only the southern part of the sky. That is only in a particular hemisphere in the galaxy. Whereas if you are sitting in USA or Europe and you are doing pulsar observations, you will be observing only the northern part of the sky, the pulsars in the northern hemisphere of your galactic plane. But in India, using the uGMRT, we are able to get, it's around 19 degrees of latitude, so north. So here, we are, from the uGMRT, we are able to see some of the northern pulsars being observed by the EPT and all, and also some of the southern pulsars. So we are in a very sweet spot geographically as well. And of course, I said we are in the best position to provide ISM noise models, which are critical when you combine data with the other PTAs. So basically, that is what happened. The Indian PTA and the EPTA, we joined hands and we signed an agreement, which is called the IPTA 3P+ agreement. So we joined our data and we did a combined gravitational wave search, combined noise modeling and combined gravitational wave search in our own data, these two data together. And we announced our results on this June 28th, actually, it's not 29th, I guess, or maybe 29th, so across different time zones. So we did these announcements from EPTA and InPTA together in a series of papers. And on the same day, there were coordinated releases from the other PTAs as well. So this was actually coordinated by the International Pulsar Timing Array committees, where we had planned to publish all our individual results, and it was coordinated to be released on the same day so that all the PTAs can do the announcements together. So the EPTA and InPTA, we released our data, and together in our data, we could see the Hellings and Downs correlation along with the common red noise spectrum to within a certain statistical significance. I won't go into all these things right now, but just know that we could see the Hellings and Downs in EPTA and InPTA data. Similarly, the other PTAs, the nanograph, that is the American PTA, USA, and the Australian PTA, the PPTA, they could also, for the first time, see Hellings and Downs correlation in their data at some particular statistical significance, which we measure in terms of the sigma, 3.5 sigma, 4 sigma, something like that. So that is what the announcement was all about. That is what, for the first time, gave us a very strong proof of the fact that there could indeed be a stochastic gravitational wave background, which could lead to all these theoretical predictions about the delay in pulse arrival times from millisecond pulsars distributed across the galaxy. Okay, so in a way, we had been using a galactic scale instrument made out of all these pulsars, which you can think of arms of your detector, located light years away from each other. So we have been using a galactic scale instrument for tens and 15s of years, for decades, to record the signals and to measure the delays. And finally, after so many years of hard work and very precise data analysis, analysis techniques and measures, are finally beginning to see the signatures of correlation or whatever signatures you expect in your data due to the stochastic gravitational wave background. So this is what all this was about. Okay. Now, I would just like to mention that I had been talking about the statistical significance. At the very beginning, I said that this was announced as a discovery. But as scientists, as astronomers, we would still be a bit careful, because when you're obtaining the Hellings and Downs curves, it's still within some error bars. And when you claim a detection, whether it is in astronomy, whether it is in particle physics, whether it's a Higgs discovery or whatever you are claiming, there is a certain confidence interval within which you have to show that you can make that claim. Okay. Now, that is the holy grail of the experimentalists. Coming from statistics, it's something we call 5 sigma detection. Now, the interesting thing, it's also expected that all the individual PTAs that have seen this Hellings and Down correlation, individually, we have not been able to cross the 5 sigma significance yet. However, we are very close to it. It's ranging from all the different PTAs they have been reporting, depending on the type of analysis that you are performing. It could be 3.5 to 4 to even 4.5 sigma is being reported. Okay. Now, it's a definitive hint that we are heading towards the ultimate juncture where we can claim with 98% confidence that it's a detection. But with individual PTA data, it's going to be very difficult. If only nanograph alone wants to do it, they have to wait for another 5 to 6 years or another decade or so. Okay. However, if we combine all our data together, say nanograph combines its data, EPTA and PTA have already combined together. Now we combine our data with the nanograph and the PPTA and the other PTAs like Meerkat and all, then first of all, we get a large number of pulsars. Indian Pulsar Timing Array had 14 pulsars. Europeans, they had around 20 pulsars. Nanograph, 25 pulsars. Nanograph had around 67 pulsars, okay, like that. But if we combine all our data together, then we get a sample of more than 100 pulsars, around 115 or 160 pulsars that can be used to do the analysis. So our sample size is increasing, which means in the Hellings and Downs curve here on the x-axis, you are getting more number of pairs to do the sampling. And that's if you can do a better sampling, you are more likely to get more precise correlation curves here. Okay, that is the simple basic idea. So what we are doing right now is we are combining our data together. In fact, as we speak, the combination is going on. And in a year or so, maybe early next year or middle of the next year, all these PTAs will come up with the results, these similar results, the common red noise spectrum and the Hellings and Downs correlation, but not on the individual data sets, but the combined data set. This is going to be known as the International Pulsar Timing Array Data Release 3. That is the third data release of the Indian Pulsar Timing Array. Two other data releases have happened earlier. So in this data release, we expect to get cross the 5 sigma detection mark. And that is when the scientific community, as a part of the scientific community, we can claim that, yes, it's a discovery, it's a detection. But anyway, media doesn't care about whether it is 3 sigma, 4 sigma, or 5 sigma. And anyway, most of the scientific community is also convinced that 4 sigma, even 3 sigma is good enough. But yeah, so as scientists, we would still like to wait for a while. And so that is the basic idea. I hope you, I know it's a difficult concept to grasp right now, but I, I just tried to explain the basic facts to give you a very basic flavor of how the detection or the evidence has been obtained. What is the instrument that has been used? How is this stochastic gravitational wave background detection different from the gravitational wave detection that has been happening since the last 8 years? Okay, and what we expect in the future. Okay, so after the gravitational wave detection, of course, there is going to be a lot of science. We are going to study the sources that are generating these gravitational wave detection. I have not gone into those slides, but just know that we have been assuming that the only source of stochastic gravitational wave background could be the supermassive black hole binaries. But actually, there could be other sources as well. There could be cosmological sources, which could date back to the very, very early stages of the universe. So these gravitational waves could actually contain signatures of the moment of birth of the universe as well, the inflation and all that stuff. Okay, all that very fancy, interesting stuff that we know of. At least we try to know. So all these things could also lead to a stochastic gravitational wave background. So once you have the detection, once you have the data, and you have theoretical models for all these different kinds of sources, you can dig through the data and try to look for all signatures of all these individual events. And that is going to bring up very, very exciting science. So these are very exciting times that we are looking forward to, very exciting times ahead for science, for all these different fields of science, whether it's cosmology, astrophysics, even for data science techniques, we are talking about ultra high precision measurements. So we need good statisticians, we need good data scientists, we need good instrumentalists for the astronomical instruments to be developed, very high resolution astronomical instruments, and good theoreticians, both in astrophysics and cosmology and even other fields. So very interesting times ahead. And I think I should stop. I have taken like almost 2 hours now. I'm sorry. Okay, so yeah, so with the last slide, I would just like to thank this wonderful team from the Indian Pulsar Timing Array. And you won't see all of them here. We had clicked this photograph in February this year in a meeting that we had at IMSc Chennai. Many members were abroad. But yeah, so I'm thankful to be a part, really grateful to be a part of this wonderful, enthusiastic team. And remember, this team does not only contain faculty members and postdocs and PhDs, it also contains of graduates and undergraduates, and ranging from streams, not only like physics, but also engineering. Okay, so it's a very, what to say, it's like a spectrum, okay, from different kinds of fields and different age groups. So any of you feel interested, any of you want to know more about it, or would like to contribute to all the interesting and exciting stuff that is going to happen over the next few years or next few decades, you are welcome to get in touch with us and explore. Thank you so much.
Thank you, Dr. Tarafdar, for this wonderful, engaging talk. Yeah, it was really nice to know about all the nuances of this Indian Pulsar Timing Array, the measurements, the observations, etc. So there are a couple of questions in the chat box. So I'd like to mention those one by one. Yeah. Yeah. Shashank asked, are gravitational waves transverse in nature?
Just a minute. Okay, it's in the chat, right?
Yeah, it's in the chat. I guess you can see it.
Yes. So, see, gravitational waves do have polarizations, but when we are talking about the stochastic gravitational wave background, it is not the gravitational wave coming from one particular source. Okay. So when you have the stochastic gravitational wave background, it is basically a superposition of all these gravitational waves that are coming in from all the different sources, which individually are polarized. Okay. But when you have the superposition, you have a random superposition of all these phases and polarizations to obtain the gravitational wave background signal. So basically, yeah, so the answer to your question is yes, so there are polarizations, but here we are talking about the background, okay? So, which is a superposition of the individual signals.
Yeah.
Okay.
That is another question from Sahil after this.
Okay, how do you incorporate these random fluctuations into the theory such that analytical calculations match the observational data? Yes, absolutely. It has to do with the stochastic. So when I tell you about the delay model, which has deterministic terms, so there are two things: deterministic and stochastic. So deterministic means you have a very well-defined analytical expression, theoretical expression, where you have variables and you have constants and you have some result. So if you know the result and if you know the variables, you can do the fitting and get to know of all the parameters. That is the usual way. So that is the deterministic part of the analysis. But when I say fluctuations, so there could be variables in your data which are not a fixed value, which have a distribution. So it is fluctuating, so it's going to have a distribution. Okay, it could be Gaussian, it could be any other distribution. So when you have in an expression variables which are not a particular value, but it's not discrete, but it's a continuous distribution. So then you are doing the same kind of a modeling, but here you are dealing with distributions of your inputs and distribution of your outputs. Okay, so what you do is you try to fit, you try to obtain the best possible fit using the statistical methods of Bayesian analysis, which I don't want to go into the details now. You can read the textbook materials there. So there is this Bayesian way of, and a frequentist way as well. There are different ways of doing the statistical fitting. So these statistical tools can actually be used to fit for parameters, fit for or obtain of the best fit distribution of a particular parameter, not a value, but a distribution of parameters using some input distribution of the variables that you're fitting called priors and the fitted distribution that you're obtaining called the post-inverse. Okay, so it's basically it's fitting and it's kind of a stochastic fitting, and that's how we obtain the random. That's how we try to model the random fluctuations. Okay, let's see a question.
Yeah,
Shubhart.
Shubharti asked.
The ISM that you mentioned has electrons. We measure the DM for a particular observation event. But even during the observation event, can the DM not change due to change in electron positions, even on the same observation that is the same DM? Yeah. Or is it because the order of length of the ISM is not of that high order for the changes to be of much significance? You're right. The thing is, ISM is always dynamic. It's always changing. Okay. But when I am observing a pulsar on a particular day, I am observing that pulsar for around, depending on how bright that pulsar is in radio, I can observe that pulsar for 15 minutes, 20 minutes, half an hour, or maximum 1 hour. That is the maximum we observe a pulsar. So usually over the length scales that we are talking about, when you integrate the ISM variations over these length scales, light year length scales, the amount of variation that would be required to cause significant changes beyond, by significant changes, I mean changes beyond the order of precision that we are obtaining. So causing these, in order to cause those significant changes in this length scale along which you are integrating, you would need even longer times. So it's not that the DM would change so significantly within half an hour or 1 hour of observing a pulse a particular day that your DM estimation would get troublesome or something. So yeah, so you are right in a way. Okay. Okay. This is another question from Sahib.
Yeah,
Bit off topic, but in your initial. Yeah, no, that's fine. It's fine. I mean, ask me questions as you like. So, bit of off topic, but in your initial slides, you mentioned primordial gravitational wave. Could you mention what those are? Well, honestly, I do not know what those are. Okay, so I am not an expert there, and even I do not know whether the experts in that field still have a very consistent theory regarding these claims. But these are propositions right now. These are all hypotheses right now. So people are thinking about all the different kind of sources that could cause these background disturbances in space-time. And one of the possible reasons is that the cosmic microwave background itself, which is a relic of the Big Bang. Now, that background radiation itself should have some signature on these persistent ripples in space-time that you have all around the universe. So these ripples, very even lower frequency ripples, those are even lower than the nanohertz range. Okay, even so when I showed that plot, that actually laid beyond the nanohertz scale. So I think you were talking about this. So the primordial gravitational waves that could be expected from the cosmic microwave background, those would fall in even lower frequency ranges. Okay. So it's not that we would get that in the nanohertz frequency range, signatures of that in the nanohertz frequency range. But there are other cosmological events that could have signatures in the nanohertz gravitational wave range, like the inflation itself, the disturbances caused in the space-time, which have caused these persistent contributions in the stochastic gravitational wave background radiation during the inflationary phase of the universe. Then there were phase transitions in the universe, which led to the slowing down of the inflation. So all these things are being proposed to probably have signatures in the stochastic gravitational wave background. As theoreticians are working the maths out, they are trying to see, and some proposals have already been there, and there is a lot of work going on where people are actually proposing that those events related to very early universes, they could have their relationships on the stochastic gravitational wave background. But the primordial gravitational wave that I showed in this figure, those would even be beyond the PTA sensitivity. Avigyan, it's your question. I can.
Yeah.
Yeah. So maybe you can just ask. I'm reading through it. But... For different sources of GWB, like the cosmological pulsar, would there be difference in the curve, the correlation curve you talked about, or how would it be in the okay? Yeah. So you mean how can we distinguish between the astrophysical and the astrophysical sources and the cosmological sources from the Helling and Downs curve? That is what is the question. No, the thing is, from the Helling and Downs curve, we may not be able to actually distinguish. Distinction is more prominent in the other criteria for the gravitational wave detection, which I have intentionally not gone into much, but that is the common red noise spectrum, which I was talking about. So if you remember, I had told that there are two things which are distinctive signatures of gravitational wave background. One is, of course, the spatial cross correlation, which is the Helling and Downs correlation. The other one is the common red noise spectrum in the delays for each pulsar. Okay. Now, it was worked out long back in 2003, Jaffe and Baker, they showed that if you assume that the gravitational wave background is entirely these supermassive black hole binaries, and if these supermassive black hole binaries in the universe have a continuous distribution, and if they have almost circular orbits, which is an eccentricity of 0, then you can actually calculate that the strain due to this stochastic gravitational wave background as a function of the frequency of the gravitational wave background would have a dependence of f to the power minus 2/3, which means the gravitational characteristic strain of the gravitational wave that would have a spectral index. We call this value the spectral index, the spectral dependence on the frequency of minus 2/3. Now, this minus 2/3 value, of course, is coming only from the assumption that the only contributors in the gravitational wave background are the supermassive black hole binary pairs. Okay, but from the data, even from simulations earlier, we have seen, and even from the data now, what we are seeing is that if we try, there is a common red noise spectrum, of course, but the spectral index of that common red noise spectrum is not exactly minus 2/3, which is expected from the supermassive black hole binary pairs. Rather, it is a bit off or lower than that value. Okay, so from simulations, actually, we have seen that in these astrophysical sources, if you start to relax some of your assumptions, like the assumption that it is completely circular orbit, eccentricity is 0, you start relaxing it, and then you try to find out what is the expected spectrum that you would get for other eccentricities, you would actually find that there is a region, there is a particular parameter space region within which of the spectral index that you can get. Okay. Similarly, you if you consider other astrophysical sources like the stellar scattering or viscous disks and all that, even then you will find a distribution. The same goes for cosmological sources. Even beyond these astrophysical sources of variation, or inconsistency that could happen in this spectral index. So that would also be coming from the cosmological sources. Now, how to distinguish? The first thing is, in order to distinguish, we need to figure out, or we need to measure, or we need to plot this common red noise spectrum. And we need to find out what is the spectral index that we are getting of this common red noise spectrum. That is the index of the frequency of gravitational waves, okay, versus the characteristic strain. Now, if we have theoretical models which are being worked out, now if the theoreticians with their models can tell us that this is the spectral index that you would expect in your combined stochastic gravitational wave background if the source is this, if the source is supermassive black hole binary, or if the source is cosmological phase transition, or if it is inflation, or whatever, so on and so forth. So when the theoreticians come up with models which would propose these ranges of the spectral indices of the common red noise spectrum, then from the data, we would be able to match the data with these models, and through that procedure, we would be able to constrain which process is contributing how much.
Okay.
Okay.
Yeah, got it. Yeah.
Great. I
Yeah.
don't see any more questions on chat. And of course, people are very tired, only 8 people on the call.
Hello, hello, sir. I have a question.
Yeah. Who is this?
Yeah, Pankaj.
Pankaj. Okay. Yes. Pankaj.
Okay, so I want to ask about, there was a theory of stochastic inflation by Alexis Starobinsky. So it was given around 1980. So many cosmologists have worked on the theory regarding the primordial black holes.
Okay. Yes.
So my question around that is that does stochastic inflation in any way related to gravitational wave? I mean, of course, it will be
Yes.
inflation. I'm talking about this cosmic inflation.
Yes.
And there are stochastic nature, or is it a sign that we are on the right path in the formation of theories?
In the right path for?
In the formation of theories, just like we, the stochastic inflation was given to, right now we discovered the stochastic gravitation with the ground. So is it like we are going in the right direction, or is it just a coincidence?
Well, I cannot tell you the answer very precisely. I mean, I can't be so sure. I mean, none of us can be so sure, neither the theoreticians or the experimentalists. But the best we can do is, as I said, to check for consistencies between the theoretical models and the data that we have. See, in data, all that we have are the residuals, that is the delay in arrival times, and all that we can measure are these correlations or these spectral indices. We cannot do anything else from the data. So yeah, so this stochastic inflation theory I'm really not an expert, so I can't really give you a detailed answer. But if the combined data, that is the data with much more sensitivity that would be able to constrain these spectral indices better, if that data matches with the range of the spectral indices that we can expect in the gravitational background from the stochastic inflation theory, if they have some sort of an overlap, then we can say that it's a strong probable candidate. Okay. But yes, I mean, in theory, I can't tell you whether it's the right direction or the wrong direction. But of course, it's a direction that is worth pursuing if you are if you are getting if you are getting signatures in the stochastic gravitational background that are consistent with the observations. So yeah, I'm sorry, I can't tell you whether it's the right way to go.
Okay.
But it's worth pursuing that. In fact, people are pursuing lots of other possibilities right now. The moment this thing came up, even years before, when people knew that this is coming up, there had been a lot of effort to explore different kind of possibilities, and we need these studies actually. Actually, we are.
Yeah, okay. So I was questioning because many of the theoreticians who predict this theory, they are somehow like view the values of the power spectrum nearer to what they have observed in the CMBs. So it was like a more consistent theory. So stochastic inflation.
Yeah, from CMB, from the CMB point of view, you are right. But if that has some gravitational wave counterpart, there's some signature on the stochastic gravitational wave background, it could be a stronger confirmatory evidence of the theory, right? So, but we need the model. We need the model, the theoretical model, a similar kind of model that would work out what is going to be the signature on the gravitational wave background.
I think the same model was used even by the primordial black hole research. So I think it was consistent regarding the data and the modeling of these. All of these were consistent.
But
so, okay, so I was working on this. Yeah.
Okay. No,
so
sorry.
I just wanted to know about this gravitational waves and this primordial black holes, because sometimes before some time there was some trending topics that this primordial black holes can be the dark matter candidates, and such type of things were given in the literature of many. So I just want to ask that these gravitational waves, do they have some link with the primordial black hole?
There could be. I am unfortunately not very aware of a theory which proves primordial black holes as the sources of stochastic gravity. But yeah, I mean, I cannot rule out the possibility, of course.
Okay. Thank you.
Yeah, thank you so much.
I guess there are no more questions from the audience.
The audience is really eager to leave now. I think people need to have their dinner also. So it's dinner time.
No, it was actually a very engaging talk. Very interesting, especially the nuance. Yeah, I'm stopping the screen recording.
Yeah, sure. Thank you.